Let's do a physics example using derivatives. And this is actually an equation that we will meet in our class later on. So let's just kind of review the ideas with differentiation that we've gone through in a couple of videos before this one. So let's say we have a position time function that looks like that. A, omega, and phi are various constants, and actually this is a real equation. It does have meaning, but we're not worried about that now. Let's determine an expression for the velocity time function. Well, we need to know that whenever we differentiate position, we get velocity. So the velocity time function is the derivative of the position time. And so what's that going to be? A is a constant, so I'm just going to rewrite that. Now, we mentioned that the derivative of cosine is the opposite sine of the thing, whatever it is. Derivative of the cosine of something is the opposite sine of that thing. So we just rewrite that. And then we said, hey, whenever you differentiate, you have to multiply by the derivative here with respect to time of whatever's inside here. Now, the derivative of phi is just 0, right? But the derivative with respect to time of this thing is omega. So I've got another omega that comes into play here, which means when we simplify this, I think I'm seeing negative omega a sine omega t plus phi. What about the acceleration time function? The acceleration time function is going to be the time derivative of the velocity. So let's see if we can do that. The minus sign and omega and a are constants, so I'm just going to leave those as they are. What's the derivative of the sine of something? Oh, it's the cosine of the thing. So cosine of omega t plus phi. And then, since we're differentiating, we have to multiply by the, in this case, time derivative of the thing in parentheses, which is another omega right there. So when you simplify this, you get negative omega squared a cosine omega t plus phi, like that. And as I mentioned earlier, these three equations, these are actual equations that we will meet and use when we get to simple harmonic motion. But that's a story for another day. Let's answer these questions. These are pretty easy, aren't they? What's the maximum magnitude of position? The position time function is up here at the top of the screen. And isn't it true that the maximum value that the cosine of anything can have is 1? And that means that the maximum magnitude of position is just a. Similarly, the maximum magnitude of velocity, what would that be? Let's look at our velocity time equation, which I'm pointing to right now. It's now at the top of your screen. The sine can have a maximum value of 1, sine of anything. So if that were 1, then wouldn't the maximum magnitude of velocity be omega times a, whatever that comes out to be? And finally, the maximum magnitude of acceleration, similar reasoning shows that the maximum value of cosine is 1. So the maximum value that the acceleration can have is given by that product right there.